Hey guys, Miss Marusik here, and in this video we're going to talk about non-STP gas stoichiometry. Now, throughout the course of this semester, we have looked a lot at reaction stoichiometry, and within that, various ways that we can convert back and forth between the moles of a substance and the volume of a substance. And the type of conversion we're allowed to use is dependent on what kind of substance we have present. For example, we have learned that if I have a pure liquid present, that I can use the density as well as molar mass to go between moles and volume. If we have a solution, we can use the molarity to get between moles and specifically liters of that substance. And way back when we first learned about reaction stoichiometry, we said that if we have a gas that was at STP conditions, standard temperature and pressure, 0 degrees Celsius in 1 atmosphere, that I was allowed to use 22.4 liters equals 1 mole to go back and forth between moles and volume. However, way back when we learned this, I had a lot of students that asked me, hey, Miss Marusik, what do I do if it's not at STP? Can we calculate that? And at the time I was like, well, yeah, we can calculate it. We just haven't learned the conversion yet to be able to do that. However, guess what? Now we have learned that conversion, and that conversion is PIV-NERT, our ideal gas law formula. You notice it has volume in it, and it has N, number of moles in it, and so we can use this to get back and forth between those two variables. So when we set up our map for these problems, it's going to look a whole lot like what we did back with molarity, where we're going to have some stoich in our map, but we're also going to have a formula, this time that PIV-NERT formula. Now they have to give us enough information to plug into PIV-NERT, and I still might need to pick out some variables, like for example, we might need to pick an R value, but this is going to be our way that we're going to be able to do these problems. All right, so to start us off with the problem here, as a reminder, the way I can tell that a problem is going to need reaction stoichiometry is the fact that they're going to be mentioning amounts of different substances, and they're going to be talking about some sort of reaction taking place. For example, here they're asking us about liters of hydrogen gas being collected, meaning that that's being produced, when I have a certain amount of zinc reacting with HCl. So I can see there's a reaction with amounts. I know we're doing reaction stoichiometry. Think about our steps for reaction stoichiometry. What was always the very first step? Hopefully we remember it's writing our balanced equation, right? So I'm going to start off here with zinc and HCl. And I want to think about what kind of reaction those would do with each other. I have an element and a compound. Remember, when I have an element and a compound, these will typically do a single replacement reaction. So the zinc is going to replace something in the HCl and kick it out and then pair up with the other substance in there. And if I look here, I know that when zinc becomes part of a compound, it does take on a +2 charge. Well, in here, that chlorine had a -1 charge, so that would make sense to pair a positive with a negative. So that'll give me ZnCl, and it'll give me 2 chlorines at -1 each to balance out with the zinc at +2. That would then kick out our hydrogen. And hopefully we remember that hydrogen is diatomic, so I want to put H2 there. And then I do need to balance this, and so I'm going to go put a 2 on the HCl. I'm not going to worry about states here because, again, states aren't important when you are only trying to do a reaction stoichiometry problem. You only have to put states if a problem specifically tells you to. All right, so next let's talk about our map. Okay, I'm going to look for how much, what is how many statement. I'm looking for how many liters of hydrogen gas. And I notice they give us some other information about the hydrogen gas here. They tell us that we have a pressure of 750 torr and that we have a temperature of 22 degrees Celsius. All right, so I'm going to go ahead and jot all that down. So I have it. I also see they give me that I have 40 grams of zinc. reacting with excess HCl. As a reminder, having excess just means that I have plenty of that to go around and that the zinc is going to be the limiting reactant that is going to limit how much of that hydrogen I'm able to produce. All right, so now let's kind of think about what do we need to connect these two things together. And hopefully we remember our bridge between one substance and another is our mole to mole ratio, utilizing our coefficients. Now, conveniently here, these are going to be in a 1-to-1 ratio, so that's going to make that step a little easier for us when we set it up in the stoich. Grams to mole, I would use molar mass. So we're going to have to look up the molar mass of zinc here in just a moment. And that'll get me to moles here. Now, again, before we said that if this was a gas at STP conditions, to go between moles and liters, I could use 22.4 liters equals 1 mole. But again, this is not at STP conditions. And so therefore, I'm not allowed to use that. So instead, what we're going to use here is pivnert. As a reminder, moles is your N. So once we do this stoich here, we would plug in the N for moles. Okay. I have a pressure. I have a temperature. I'm trying to solve volume. So the only piece I'm really missing here is R, and that's our gas constant that we can get off our formula chart. So thinking about that for a second, I notice that the pressure is in torr. So when I come over here to my R variables, I notice that the one that has torr is 62.4. So that's going to be the variable I'm going to use here. So 62.4 liters times torr over moles times Kelvin. And I'm going to make sure that all my units match up. Obviously, the torr matches up. The liter conveniently matches up. I don't have to do any kind of converting there with that. Moles will match up once I do my stoich and I get my answer for that. Kelvin does not match up. So guess what? We need to convert that really quick. So I'm going to have 22 plus 273, and that gets us 295 Kelvin. Okay, so I kind of have everything laid out here, and so now I'm ready to actually solve this problem. So on this one, because this is my starting number here and I'm working this direction toward the question mark, I'm actually going to start out with the stoich steps here. So I'm going to start off by asking myself, well, hey, how many moles of H2, which remember is our N that we're looking for, can I get out of the 40 grams of zinc? All right, so now we're going to start with our stoich steps here. If grams of zinc is on top, I want grams of zinc on the bottom. I'm trying to get this into moles of zinc. That is 1 mole of zinc on a molar mass step. I need to look at my periodic table here. I see that zinc is 65.39 for our molar mass. And now I'm going to do my mole to mole ratio. So 1 mole of zinc on bottom to cancel out that unit for every 1 mole of H2. Now I will warn you, I have seen a lot of people start to get lazy on their units on stoich. Please don't get lazy on these units. Here it's a 1-to-1 ratio, so it was pretty easy to see where those numbers needed to go. But when it's not a 1-to-1 ratio, I saw so many people on our last test flip-flop those numbers because they flip-flopped the units because they didn't write them, okay? So be very careful there. All right, so I can kind of see here that obviously the ones don't do anything, so really what I end up here with is this 40 grams that ends up getting divided by the 65.39. Oops, there we go. All right, now I'm not going to worry about writing this whole thing down here. I'm just going to kind of round it off for sig figs. I see everything kind of has 3 sig figs in my original problem. So for right now, I'm going to put 0.612. If you want to use more digits right here, you can, but I'm going to show you a trick here in just a minute that we can do. All right, that is going to be my moles of H2. That again, this is my N that I want to plug into pivnert. So now I'm ready to plug into pivnert. And this is where I'm going to go back and use some of this data up here. So the pressure was 750 torr. The volume is what I'm looking for, so that's our unknown. Our N is going to be that 0.612 that we just solved. The R is what we picked, the 62.4. And the temperature is 295. All right, now I'm looking for V. It's in the numerator, so it's in a good spot. I want to leave it where it's at, but I want to isolate it, meaning I need to get the 750 to the other side. So to get that to the other side, what we're going to do here is multiply this one part together. Now what I'm going to do is I'm going to use my previous answer that I had in my calculator. So this will use the previous answer that we just calculated for moles instead of plugging that in, times 62.4 times 295 divided by my 750 to get that over. So again, the way to undo this multiplying here with multiplying by 750 is to divide it over. And rounding for sig figs, again, for 3 sig figs, this is going to get us 15.0. And let's think about what we were trying to solve. We were trying to solve volume, and we were trying to do so in liters because that's what matched up with our unit within R. And that was for H2. So theoretically, this is the max we should be able to collect. This is our theoretical. As a reminder, when we actually do this in lab, we may not collect all that much, but at least it gives us an idea of how much we could potentially collect. All right, let's do another one together. We're going to go through this in a little bit faster here. It says here that we have sodium carbonate decomposes with heat into sodium oxide and carbon dioxide. So first thing I'm going to do is I'm going to write myself a balanced reaction here. Sodium is Na with a positive 1 charge. Carbonate is CO3 with a negative 2 charge. So that's going to be Na2CO3. Decomposition means that this is going to break apart. Since it's not doing so into elements, they've told me what it's breaking down into. Sodium is Na with a positive 1 charge. Oxide is oxygen with a negative 2 charge, so that's going to be Na2O. And carbon dioxide is covalent. That's CO2. I just use the prefixes to help me know what that formula should be. If I kind of glance at this here, it actually comes out balanced. That doesn't happen all that often, right? So that means everything here is going to be in a 1-to-1 molar ratio. All right, next I'm going to start setting up my map here. I see here I have 450 milliliters of carbon dioxide. Are collected, and they give us some other information about it. They tell us we have a pressure of 800 torr. We have a temperature of 45 degrees Celsius. And it wants to know how many grams of sodium carbonate were decomposed. And again, we're assuming here that this was 100% yield because they didn't tell me otherwise. All right, so let's kind of start thinking here. I know to get grams of this, I'm going to need to use this guy and kind of work my way over. So I need a bridge between these two substances. And of course, that bridge is our mole-to-mole ratio. Now here that mole ratio is just going to be 1-to-1 because those are my coefficients. I also need to get back and forth between grams and moles. This is going to be molar mass. Now this time, here is our question mark. This is what we're trying to find. So this is going to be kind of our end result here, meaning we're working in this direction. So back over here, I want to figure out how can I get this milliliters into moles? Well, again, it's not a pure liquid, so I can't use density. Plus, they didn't give us density information. They didn't give me molarity information because this is not a solution. It is a gas, but it's not at STP conditions, so I can't use 22.4. So my only option here, being a gas at non-STP conditions, is PivNert. Now, what we're going to be trying to solve here is moles, the N. Because if I have moles, the N, then I can use that as my starting place to then do these next two steps of stoichiometry. that means that I'm going to be plugging in this 450 for my volume. We're going to evaluate its unit here in just a minute. I have a pressure also and a temperature, so what I'm missing is my R value. And again, I see that we're using torr here again, and hopefully we remember from the previous problem that when I have torr, my R is going to be that 62.4 liters times torr over moles times Kelvin. Now, obviously, both of these happen to be in torr, but these could be in any unit, atmospheres, kilopascals. You're going to solve it all still the same way. All right, I want to make sure my units match up with this. And I'm like, okay, well, obviously torr matches up. Moles also matches up, but I notice the volume does not match up. So as a reminder, milli, I need to move that decimal point 3 places to right here in front of the 4 in order to convert this into liters. I also, to my temperature, need to add 273. So I'm going to have my 45 plus 273, and that gets 318. All right, so here, because this is my starting place, I'm going to actually be plugging into PivNert first, okay? So let's set that up here. I'm going to have PV equals nRT. Our pressure is 800. Our volume, we converted to 0.450 liters. My N is what I'm looking for. My R is 62.4, and my temperature is 318. Again, all those units are going to work themselves out as long as you made sure everything matched back here, okay? I see that I want to get N by itself. Right now, N is in the numerator, so that's a good spot. I don't have to worry about getting it out of the denominator, but I do need to get it by itself. So what I'm going to do is I'm going to multiply the things together that are on the opposite side. So I'm going to do 800 times the 0.450. And then I'm going to get these two guys to the other side. Now to do that, because this is all multiplied here, I'm going to divide them over. So I'm going to divide by 62.4, and then I'm going to divide by 318. And that gets us this number here. Now I'm going to go ahead and round it to some extent, but you'll see I'll kind of use the trick I showed you a minute ago in my calculator when I calculate the next part. So I'm going to write 0.0181 moles, and this is right now of CO2. All right, so now here's the deal. On this next part, when I actually do the stoich, I want to figure out the grams of Na2CO3. But my starting place is going to be this guy right here. All right, so obviously I want to get our mole to mole ratio now. Luckily for us, this is a 1-to-1 ratio. 1 mole of CO2 for every 1 mole of Na2CO3. I still need to show it though, okay? So don't forget, you still got to show it with units to get that credit, okay? So now I need my molar mass, right? So we're going to bring down mole of Na2CO3. Oop, I didn't leave myself a lot of room there, did I? All right, and we're going to convert this into grams. As a reminder, when I do a molar mass step, 1 always goes with moles, okay? Oh, I almost forgot. I'm not going to be able to do my trick because I have to plug something in here. So I'm going to make sure I leave that in my calculator so I can use it. So I need to get my molar mass of Na2CO3. So I'm going to bust out my periodic table here. 22.99. I'm going to times that by 2 because there's 2 of those sodiums. Then I have carbon, which is 12.01, plus O3. Oxygen is 16. And there's 3 of those. So that gets us a molar mass of 105.99. All right, so now I'm ready to plug all this in. And this is what I was talking about. Since I just had to calculate that, I can't just use the answer from the previous one as my start place. So I'm going to plug a little bit more of this in just so that way I can make sure I'm not rounding too much. Okay, so that's probably enough, okay? I usually kind of put a little bit extra in there just so that way when I cut off for sig figs at the very tail end, I'm not cutting myself off too short. All right, so now I'm going to have 1 over 1, which if you want to put that in, you can, but obviously it doesn't do anything. And then I'm going to multiply by 105.99. So I'm going to take this and multiply by 105.99. And that gets us an answer of 1.92 when I round for 3 sig figs. So here at the very end, I can go ahead and round for that 3 sig figs. Don't freak out about sig figs, y'all. I know I've been kind of emphasizing it here, but if you show a couple extra, like 1 extra, or you show 1 less, we're not going to squabble about it. You just don't want to cut it off too short, you know, like there's a limit to it. I honestly, we'd rather you show extra than show too few. So, all right, so our unit is going to be grams, and we were solving grams of Na2CO3. So there it is. All right. Okay, guys, there's one more problem here. Potassium chlorate decomposes with heat into potassium chloride and oxygen gas. You have 7.89 grams of potassium chlorate heated until it decomposes. How many liters of the oxygen gas will be formed at 700 torr and 25 degrees Celsius? So again, we can see some non-STP conditions. So here's what I want you to do. I want you to take a moment, pause this video, and try out the problem, okay? All right, go ahead and pause it. See if you can try it out. All right, did you pause me? I hope you did. I hope you tried it out. Guys, if you're just copying this, it's going to be a hot mess express for you. I'm going to tell you right now. Make sure you know how to do these, okay? All right, let me go ahead and put my work up here. Let me scooch this up just a little bit so it's a little bit easier to see here. All right. So first off, my balanced reaction, I had 2 KClO3 decomposing into 2 KCl plus 3 O2. So yes, we still need to know how to write and balance reactions. It's still important, right? Okay, so then I started off with my map. I said, hey, I have 7.89 grams of KClO3. I'm trying to figure out how many liters of O2, but they did give us some other information about O2. They gave us our pressure and our temperature, so I wrote those down. And then I said, well, hey, I have grams of KClO3 over here. I'm trying to get to O2. What's my bridge between those two? And that's our mole ratio. So, of course, I had to go between grams and moles here utilizing the molar mass. Over on this side, I'm going to be utilizing PivNert. Now, because here we had the starting number with the thing that did not need PivNert, that meant we were going to do stoichiometry first, and then our PivNert would come second. So you can see we've kind of seen both problems, one where we had to do the PivNert at the beginning, and this one where we have to do the PivNert at the end. So it really just depends on the direction that the problem is headed in. All right, so then I said, okay, well, let's go ahead and do the stoich. So I did my grams of KClO3 starting place here. I then did a molar mass step. Your molar mass of KClO3 is 122.55. Then I set up my mole to mole ratio, and again, guys, if you're getting lazy on your units, it is really easy to accidentally flip-flop that 3 and 2. So please be careful. Make sure you're not getting lazy on units, okay? All right, so then I plugged that in, and that got me right around 0.0966. And so then that will be my moles, my N value to plug into PivNert. I did use 62.4 again because the pressure was in torr. I did convert my temperature to 298 Kelvin. And so then I just plugged everything in, solved for the volume, and here that got 2.57 liters once I rounded to 3 sig figs. All right, folks, that's it for gas laws. Holy cow, right? Crazy that we have finished these notes and finished the new notes for the year. I know we're really excited, right? I know we're all ready for summer, so. All right, guys, I hope you're feeling good about this. In doing these stoichiometry problems, make sure you're showing your steps, make sure you're showing your work, and you should be okay. All right, if you have any questions or need any help, please feel free to email me. Bye, guys.